Hi there, welcome to the Ephemeris podcast. I'm your host, Aphelion, and it's nice to be back for the third episode of the new chapter and the new season. If you're new and you're not familiar with our new chapter, new season, we go over 3 articles per week and discuss some of the more contemporary findings and news in the world of astronomy today. And so the first article is going to be about the Magellanic Stream. The second one is going to be about what shuts down a galaxy star formation, and a very recurring theme in this season is the curvature of spacetime, and we're going to talk about that again with a little bit about why the smallest black holes bend spacetime the most. So let's get straight into it. I actually don't have much to say other than that. Views on these episodes have been pretty high, and I hope you guys are enjoying. So let's get into it. The first story is about the Magellanic Stream. When we talk about the Magellanic Stream, we obviously need to know what the Magellanic Clouds are. So let's discuss that first. The Magellanic Clouds, we're talking about 2 objects here, the small Magellanic Cloud and the large Magellanic Cloud. Both of the Magellanic Clouds are irregular dwarf galaxies, so they don't have a distinct shape and are very small compared to other galaxies like the Milky Way. The fact that they are irregular is debated because people have noticed bar and spiral structures before upon further observation. So, it could very well be spiral dwarf galaxies, but that one is not clear. I'm just going to go with the title that it's identified with the most. So, that's a very brief description of what it means to be an irregular dwarf galaxy for these 2 clouds, but there are some other characteristics that I should mention. Apparently, only a fraction of their gas seems to have coalesced into stars, and that might be a little bit misleading because it's not like these clouds don't have gas. They're actually gas rich and metal poor, so you might consider it a population 2 type galaxy. The Large Magellanic Cloud hosts the Tarantula Nebula, which is the largest star forming region in our local group of galaxies. It just seems that proportionally, for how much gas it has versus how much gas is actually forming into stars, that fraction or proportion is quite small. So, a bit of a far-fetch would probably be like, we could attribute this lack of star formation to the fact that the clouds are less massive, but as I talked about, that could very well be misleading. But that's the fact of the matter, and the main key point that we should know about the Magellanic Clouds going into this article we have today is the fact that the clouds seem to have neutral hydrogen streams connecting each other and connecting themselves to the Milky Way, which was, I believe, evidenced by radio imaging. And the Magellanic Clouds are also known as satellite galaxies, so that makes them ones that orbit the Milky Way, which would be their host galaxy. So that gets us right into our story here, the Magellanic Stream. The stream of hydrogen gas that connects the Magellanic Clouds specifically is known as the Magellanic Stream, and the contents of the stream other than this are a continual mystery, but we seem to have made some progress with the article at hand. It tells us that scientists have found stars in the stream, which gives us a lot of information about the star formation going on in the cloud. The reason why this finding gives us crucial information is because, pragmatically speaking, the potential of gas from the Magellanic Cloud to become a star seems kind of unclear because we've talked about, the Magellanic Clouds are less massive than the Milky Way, but they have a whole lot of gas, but it hasn't turned into stars, proportionally speaking. And we have neutral hydrogen, which is not as well known as ionized hydrogen and maybe H2 regions, which would make perfect star factories. So yeah, the fact that we found stars and some of the logic behind it, which I will discuss in a moment, really clears the air here. The first quote I'll bring up is, quote, astronomers think the gas that makes up the stream was torn from the dwarf galaxies by the gravitational pull of the Milky Way. The new observations may reveal more about the stream's nature and assist scientists who seek to understand how it interacts with our galaxy. As of now, scientists say the stream appears to be sort of falling into the Milky Way. And this quote obviously supports the idea that the Magellanic Clouds are satellite galaxies and really incorporates that fact into understanding what's really going on with the Magellanic Stream and what's going on in it. So another quote here, which is really about what's happening in the Magellanic Stream, is scientists think that as hydrogen gas from the stream falls into the Milky Way, it creates the right conditions for star formation. By analyzing the data, the researchers also found that the stream is about twice as massive as they thought, which means that much more gas must be getting devoured by the Milky Way than previous calculations had suggested. So yeah, I think that's just kind of nice to know because obscurity obviously isn't pleasant, right? You'd like to know what's really going on in these mysterious streams that are between these Magellanic Clouds that are so close to us yet we know little of. So yeah, another quote here that I will mention that brings in some bigger implications. Quote, by better constraining the mass of the stream and by gaining a better understanding of the Magellanic Clouds, astronomers will be able to better estimate the mass distribution of the entire Milky Way, the scientists said in the statement. And yeah, maybe that might bring a little bit of clarity to relative masses of galaxies, because not something I didn't mention is the fact that estimates say that the Large Magellanic Cloud is like 1/10 the mass of the Milky Way, but this tends to create like complications, or like it tends to be a misleading number because the Large Magellanic Cloud is like one of the biggest in our local group, and the fact that you're saying it's 1/10 the mass of the Milky Way might make that a little bit of a weird situation. So there's a bigger implication on the findings here about the Magellanic Stream. And yeah, there's another quote actually that has even more bigger implications, I guess. Quote, much of that mass is in the form of dark matter, and I believe we're talking about either the Milky Way or the Magellanic Clouds, a poorly understood gravity exerting substance, the scientists said. Better gauging the mass of our galaxy out in its distant hinterlands will aid in accounting for ordinary matter versus dark matter contents, constraining the possible properties of the latter. So yeah, when we are looking for dark matter, we're looking at the distribution of mass in a galaxy, because that's where we believe dark matter is going to be the most detectable. And if we don't figure out what the Magellanic Stream is, that's going to kind of throw us off a little bit. So if we're more clear on it, then we'll be able to figure out dark matter a little bit better. So yeah, that's pretty much everything I have for the article on the Magellanic Stream. Let's move on to our second story, which is a really nice segue, actually. It's about what shuts down a galaxy's star formation. We talked about two galaxies with maybe less star formation than usual, but let's talk about when it completely shuts down. This is an article that was published in 2020, which is kind of old, but not irrelevant. And it talks about galactic evolution using discoveries in the aftermath of Hubble's work. We've talked about Hubble before on this podcast, and we'll be talking about his tuning fork. So I'm not going to make you rewatch the episode just to figure out what Hubble's tuning fork is. I'll give a description, but I guess if you were to watch that episode, it would be a nice prelude to this article. So Hubble's tuning fork is really where ideas about the evolution of galaxies began, because he was the one to discover that Andromeda is way too far away from us to be a nebula. It must be something else, and that's sort of where the discovery of galaxies kicked off. So he had a tuning fork, and it was a diagram that displayed types and subtypes of galaxies, which, if you looked at it visually, would imply an evolution of galaxies from elliptical to spiral galaxies, which is not accurate. Now, which is, something we now know. And the article talks about how the evolution of galaxies has changed from being about shape and structure, when Hubble's tuning fork was a popular model, and sort of shifting from that to being about star formation inside of the galaxy. And in this matter, brings up the findings of the Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey, which is the most long and I guess you could say nerdy name ever. Like, imagine somebody like just casually bringing up the Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey. I feel like it would sound very, very weird to say that, and very nerdy. So anyways, these are the findings that we're going to talk about in this article, and it's going to tell us about what shuts down a galaxy star formation, and sort of what that tells us about the evolution of a galaxy. And so some quotes that I will pull here to summarize the findings that were in this survey. Quote, the research team found that more diffuse galaxies, such as the Milky Way, have longer periods of star production than more compact galaxies. This is true even when two galaxies have the same overall total mass. More diffuse galaxies take longer for their central region to reach a critical density, and it is at this critical density that star production drops off. So we have a little bit of an answer here to our question, what shuts down a galaxy star formation? It has to do with the central region, and when it hits a high enough mass per volume that it becomes difficult for stars to form. Since the central density of a galaxy is a good measure of the size of its supermassive black hole, this finding supports the feedback model of galactic evolution. According to this theory, the galactic evolution is driven by the central black hole. As the black hole forms, a dense central region forms with it. But as the black hole grows larger, it heats the central region to the point where gas and dust are pushed away, stripping the galaxy of the material it needs to create new stars. So that's our full answer. The central region is defined by a supermassive black hole that, when it gets large enough, will start to push away star-forming material and sort of subside, I guess, the star formation. In small, dense galaxies, this transition happens quickly, while it happens more slowly in large, diffuse galaxies. While there's more research to be done, this feedback loop seems to be the most likely. So it seems that while supermassive black holes give birth to galaxies filled with stars, they also push galaxies to their dim and red demise. So yeah, that's just the essence of the Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey, which tells us a lot about star formations in galaxies and their evolution, which has come a long way since Hubble's tuning fork. So yeah, I think that's a good place to leave that article behind and go on to the third story, which is the curvature of space-time around the smallest black holes. Not much introduction is required here because we've run the ideas of general relativity to the ground at this point. Black holes are gravitational singularities where not even light can escape the curvature of space-time, and it might be intuitive to believe that the greater the mass of a black hole, the more curved space-time becomes. However, there is something to address about such a claim, and that is the purpose of the last article we will talk about in depth today. It's not necessarily the proximity to a mass or the total amount of mass that determines how curved space-time is. It is more so about the density of an object. Therefore, the most massive black holes don't necessarily curve space-time the most. It's the densest black holes that curve space-time the most. And if you have a large amount of mass, but the radius is large too, for example, that might not compete with other denser black holes in terms of most curvature. That's pretty much what we're saying here. Also, I should mention, because you're able to approach a black hole with smaller radius closer than others, it creates a greater gravitational lensing effect. So that will sort of influence how we view the space-time curvature of a black hole. And so, for the reasons I just talked about, smaller black holes end up bending space the most. And the reason why they do is because even though certain things about a black hole scale up with their mass and size, like the escape velocity and what else is mentioned in the article, the mass and radius relationship and stuff like that. There are two key parts that do not scale with mass that will make smaller black holes actually better at bending space-time the most, and they are tidal forces and more Hawking radiation. I want to allow the article to explain some of these ideas because I just thought they did a great job at it, and I wanted to bring it up here. Quote, wherever you have space itself, you also have the laws of physics that exist in our universe, which includes all the quantum fields that underlie reality. These fields all exist in their lowest energy state when they permeate empty space, a state known as the quantum vacuum. The quantum vacuum is the same for everyone so long as they're in empty, uncurved space. But that lowest energy state is different in places where the spatial curvature is different, and that's where Hawking radiation actually comes from the physics of quantum field theory in curved space. Far enough away from anything, even a black hole, the quantum vacuum looks like it does in flat space. But the quantum vacuum differs in curved space and differs more dramatically where space is more severely curved. So I like how they explained it here because I know we talked about how Hawking used the physics of quantum field theory in curved space to generate this idea of Hawking radiation really briefly, but here it's explained more in depth, so I wanted to bring that up. And just to hit it home, quote, curved space isn't just about how much mass you have all in one place, because what you can observe is limited by the presence of an event horizon. The smallest event horizons are found around the lowest mass black holes. For metrics like tidal forces or black hole decay, being close to a central singularity is even more important than your overall mass. So, yeah, I mean, that's pretty much all I got to say about this article. I feel it's quite self-explanatory because it clarifies a very minute detail about the curvature of space-time around gravitational singularities like black holes, and sort of rewrites the idea of Hawking radiation in a way that brings more clarity to the idea and makes it less oversimplified, as the article said. So, yeah, that's all I got for the third story and this podcast episode. If you all enjoyed the discussion of these three articles this week and you enjoyed the episode, please make sure to subscribe on YouTube if you are new and follow on Spotify if you're new and you enjoyed. And yeah, if I go on any longer about liking and sharing, I'm going to get really redundant. So yeah, until the next week, I will see you all later. Peace.